The lab we're doing today is lab 6. Last week we didn't do the lab because I wasn't here. And so you had problem solving instead, which I assume that all man was sarcastic. So before we get started, I want to go over the problem with collision that I was going to do in class, just so we can make sure that I have gone over a collision problem with you. So this is an example of a collision. Now, with the collision, you notice we have the officer here measuring out skid marks. Why does the officer measure out skid marks? Okay, so the collision.
To calculate the speed going to the crash.
Okay, to calculate the speed going to the crash. The skid marks allows him to determine, okay, the distance that the force of friction was at the maximum. Well, the maximum for kinetic friction is this long. So taking the mass of the car and the coefficient of kinetic friction between rubber and asphalt, they can use that to calculate how much work was done by friction. So that work that was done by friction is going to reduce kinetic energy. So if they know how fast the car was going at the time of the collision, then they can use that skid mark to determine how fast it was going before the collision. So you have the first thing, somebody realizes something's wrong, they hit the brakes, they skid, then they hit the car. During the collision, the net external force of horizontal direction is not zero, but the collision is very short in time, and the force of friction is really small compared to the force that's crushing metal parts. So they treat the collision as being a completely elastic collision, or not completely elastic, as having momentum conserved. That was a really big mistake on my part. So the collision is going to have momentum conserved. And then after the collision, if they stick together, what kind of collision is it going to be? Inelastic. They stick together, that's completely inelastic. And then they will measure how far it skidded with the two of them together. If they did stick together, they measure how far each one traveled. And they know that after the collision, then they can once again use the distance of the skid and the coefficient of friction and the mass of the car to determine how much work was done after. So in the end, they start at the end. This car ended here. It skidded this far after the collision, so this much work was done from after the collision till it stopped, so it had this speed right after the collision. Second car, it ended here. This much work done by friction, so this was its speed after the collision. Then they take those two speeds or velocities because the direction is involved, and they use conservation momentum to get what the velocities were before the collision. And then they use the skids to get how fast each car was going before somebody realized, oh crap, bad things are going to happen and hit the brakes. So that's why they come out there and they measure the skids. And you can see this here is just an example of, skid mark where somebody definitely had a bad day. So looking at the problem. Car 1 with mass of, it gives the number, is driving down the road with an initial speed of basically 56 miles an hour. I put it in meters per second to make my life easy. Car 2 with this mass is speeding and hits the brakes, skidding this far before rear-ending car 1. Why did I do that? We're keeping our collisions one-dimensional. Two-dimensional collisions just adds a little more sophistication, difficulty, if you will, to the solution. So we're keeping them one-dimensional. So rear-engine car 1, after the collision, they stick together. So I asked you this before, everybody answered correctly. That means it's a completely inelastic collision. And they skid for a distance of 150 meters, and then it asks how fast was car 1 traveling before the collision. So now we will work this problem going backward. So we start with the two cars skidded. There's the coefficient of friction. There's the distance they skidded. There's the masses. So we can take, for our first step, the work non-conservative is equal to minus force of friction times distance 2. Why is there a minus sign there? Because of the direction. Because the friction was pointing the opposite direction that the car was sliding. So that's why there's a minus sign. For the force of friction, in this case, we're assuming a horizontal road, which means that the only vertical forces are force normal up and force gravity down. Hence, the application of Newton's second law is trivial. The net force in the vertical direction is force normal minus force gravity is equal to 0. Hence, force normal equals force gravity. So M1 plus M2, because they were stuck together. So that's my work non-conservative, and I forgot the minus sign. Oh, that would give you a bad problem if you put the minus sign. So work non-conservative, what's it equal to according to the work energy theorem? Work energy theorem says that was beautiful. The work energy theorem says the work non-conservative is equal to the change in kinetic energy plus the change in potential energy. So the cars weren't changing elevation, hence the change in potential energy is just 0, and it's going to be changing kinetic energy in this case. So change kinetic energy is going to be kinetic energy. Okay, so we have to specify our states. State 0, cars at initial speeds. State 1, cars collide. State 2, cars start sliding together. And state 3, cars come to rest. I'm defining these explicitly so I can use some subscripts that make some sense to me. So at state 3, what was the kinetic energy? 0, because they're at rest. Kinetic energy is the energy in motion, 1/2 mass times speed squared. So in state 3, I had kinetic energy 3 equals 0, and we're not even worried about the potential energy because it's all staying horizontal. In state 2, the cars were moving at the same speed, so it's going to be 1/2 mass 1 plus mass 2, speed 2 squared. I'm going to change colors here. State 1 is just before they collide, so it's going to be they have different, I need speed 1A and speed 2A. Actually, let me put these. So the 2 is car 2 and B is representing state 1 here. So I have the 2 cars at different speeds, hence I have that. And then, thank you. Kinetic energy initial, 1/2 M1 V1A squared plus 1/2 M2 V2A squared. Okay, so those are my kinetic energy terms for each state. I also need my momenta going between state 1 and state 2 because state 1 and state 2 is before, the cars collide at the beginning of state 1, cars finish their collision is the beginning of state 2. So momentum 1 is equal to so there's my momenta. So now, working this problem backward, I've already started, but I need to make sure I had some definitions. We can take the work energy relations here. So we have this work non-conservative is equal to the difference between kinetic energy 3 and kinetic energy 2. The final was 3, the initial was 2. And so putting that in, I get an equation that says excellent. Please stop. So this equation, notice the 0 was kinetic energy 3 there. And then minus kinetic energy 2. I have M1 and M2 on both sides. It doesn't even matter what the masses of the cars are for this step, because the masses of the cars actually cancel this step. And I can solve this for V2 to find that. Just multiply both sides by 2 and divide by M1 plus M2. And so square root both sides. And I have speed that both cars were traveling after the collision. Now I'm going to go to before the collision. And so I'm going to go from state 1 to state 2. What condition can I use to relate state 1 to state 2? I've already said it, so it's asking you to think back to what I said. It's during the collision. What condition do we have during the collision? The answer is during the collision, because the collision is very short and the force between the two colliding cars is very large compared to the force of friction, we can treat it as momentum is conserved. So now, we already know V2, and we were given V2B, because this one here, oh wait, no, V1, we were given V1B. V1B. Yep, that's right. So we know V1B and we know V2, so we use this to find V2B. And now we have an equation to give us the speed of car 2 just before the collision. And then the final step to determining how fast car 2 was traveling before he hit the brake, so we can determine how big to make his speeding ticket, is to relate the work energy between state 1 and state 2. And so work energy between state 1 and state 2 is going to be, which car do I care about for this part of the calculation? I don't care about both of them at this point, because one car is traveling at constant speed. Right, car 1 is traveling at constant speed, car 2 is skidding. So which car do I care about? Car 2. So I'm only going to use work energy relation for car 2 for the final step. let's see, I called, okay, I used D, I should use D, oh, I did have D2 there. It wasn't a mistake. So try to skip the distance D1. So this is the force of friction times D1 is equal to the kinetic energy just before the collision, which is minus at the beginning. And so now at this point, the only thing I don't know is the V2A. And so I need to multiply everything by 2 and divide by M2. Notice the M's cancel out again. And so square root both sides. And now we have the equations. It takes a lot of math to combine them now because you got to put in numbers and put in. But we have equations to calculate how fast car 2 was going before he hit his brakes. So we can determine how big the ticket needs to be. That's the kind of problem that the police officers are doing. Of course, are they doing it like we just did it? What are they doing? They're putting it into a computer that's already done all the, has all the equations in there. They just put in the variables, so they put in mass of car 1 is this, mass of car 2 is this, coefficient of friction is this, distance 1 is measured to be this, distance 2 is measured to be this. That's what they're doing. And all of the equations are already worked out by who? Somebody who's taking general physics. So that is kind of a difficult problem, wouldn't you say? Okay, thank you. It's kind of a difficult problem. It's not straightforward. It's not a one-step problem. On the test, I'm not going to give you a problem that has this many steps. Because you screw up on one step and you could be there for 2 hours just trying to figure out what went wrong. So I won't give you one that's involved in the test. But the process needs to be something that you can think your way through, because you might get a situation that has something relevant like this. Oh, we had a collision and then this happened. What happened during the collision? What happened before the collision? What happened after? So during the collision, what should be conserved? Momentum. Momentum will always be conserved on a system that has a collision, assuming the collision is for a very short duration. Now, if the collision is, I come walking very slowly, and I bump into the torso, and I push it for a few seconds here, well, you're not going to say momentum was conserved during that collision, because it was pretty long, and I pushed on the ground during the collision. If there's no force parallel to the motion, no matter how long the collision is, momentum is going to be conserved. But since I was pushing on the floor parallel to the motion, no dives. So you have to think things through to establish, is momentum conserved here? Why? Then, what about kinetic energy? Is kinetic energy conserved during a collision? Sometimes yes, sometimes no. Okay, so we're going to do 2 types of collisions. Here's one type of collision. Car comes, magnets repel, they never even touch. In this case, assuming that the friction on this track is zero, but assuming the friction on this track is 0, then there was no horizontal force to do a work non-conservative. We had no deformation with the cars, so we should have had kinetic energy conserved. Now, you notice the cars being the same mass, they just exchange velocity in that case, which is really cool. But if they're not the same mass, that's not what's going to happen. I'm going to have a lighter car hit a stationary, heavier car. What do you think is going to happen? What?
Not going to move as much.
Which one won't move as much?
The heavier one.
Okay, the heavier one won't move as much. What's the lighter one going to do? Bounce back, right? It's just like if I run into the wall. The wall won't move very much, but I'll bounce back. So, okay, did you hear them hit? If that happens to your experiment, you gotta throw it out, because when they hit, then you're gonna have some energy loss because of that hitting. That's not part of what we're doing. So I got to go a little slower. There you see it bounce back, that one went off. And the speed of this one is less than the initial one. Now I go the other way, if I have the heavier one hit the lighter one, so this is like, this is my example. If the person's standing up and he doesn't see me coming, and I just barrel into him, I don't want that. Am I going to stop? Nope. What course are we going to do? He's going to shoot out faster than I was when I hit him. So, okay, so once again, I came too fast. You see that the light part went off faster than the heavier part was moving before it hit. And of course, we got the two cards moving. Well, it's some combination there. So what we're going to be doing in lab days, we're going to be exploring this. Now, one thing I'm going to guess that Keith didn't show you this. When you're dealing with collisions, you of course need to identify if it was elastic or inelastic. And if the collisions are inelastic, when we say inelastic in general physics, what do we really mean by those words? They stick together. We mean completely inelastic. They stick together. So that means V1 final equals V2 final. So we have a math equation for an inelastic collision. It's so easy, I usually don't write it. I didn't write that equation in my work here. I just said mass 1 plus mass 2, V2, because it had the same final speed. So that's our condition for inelastic. For elastic, it's actually much more sophisticated. Kinetic energy is conserved. So that means you're going to have 1/2 mass 1 V1 initial squared plus 1/2 mass 2 V2 initial squared equals 1/2 mass 1 V1 final squared plus 1/2 mass 2 V2 final squared. That equation is really not fun. Why is it really not fun? Because it has all those squared speeds. Well, we're going to simplify this, and what's the first obvious step to simplify it? Each one has a 1/2, so let's multiply them all by 2. That's the first obvious thing. Multiply them by 2. So, of course, that just gets rid of all the 1/2s. The second thing is not obvious. The first time, for some reason, when I was in college, my teacher didn't teach me this. So the first time I'm teaching this, I'm reading it in the textbook before I go teach it. I'm like, what? The first thing you do is you move them so you have cart 1 on one side of the equation and cart 2 on the other side of the equation. So I'm going to have m1 v1 0 squared minus m1 v1 final squared equals m2 v2 final squared minus m2 v2 initial squared. Now, if you look at that, notice this one has, on the left-hand side, I have the initial squared minus the final squared. Right-hand side, I have the final squared minus the initial squared. That was just because of moving them across. And you're probably still saying, why? How many people are saying, why? Really? Does this only make sense to you? Because, I mean, to me, it was like, I don't understand why they're doing this. You factor out the M1, factor out the M2, and then we expand the V1 0 squared minus V1 final squared. You probably learned to do this somewhere in high school math. It may very well have been lost from memory at this point. V1 initial squared minus V1 final squared is the same as V1 initial minus V1 final times V1 initial plus V1 final. With the minus and the plus, the cross terms add up to 0, and you just left with the two squares. Do the same on the other side. And now we have an equation that looks like I've just made my life harder. But not really. Not really, because we still have our conservation of momentum. Conservation of momentum said V1 initial, well, M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Moving the masses, moving the carts to opposite sides just like before makes this M1 V1 initial minus M1 V1 final equals M2 V2 final minus M2 V2 initial, or, and this is where finally things make sense, factoring out the mass. Notice now, this and this are the same. This and that are the same. So that's like saying 5 times this is equal to 5 times that. I can divide that out. So if I divide out M1 times V1 initial minus V1 final from the left side, and M2 times V2 final minus V2 initial on the right-hand side, I'm left with, for conservation of kinetic energy, the relationship that V1 initial plus V1 final equals V2 initial plus V2 final. That's the net equation we get at the end if we had an elastic collision. The speed before and after for car 1 is equal to the speed before and after for car 2, which is a really kind of surprising outcome, I think. And so we have conservation of momentum, the equation right here. Okay, so I'm going to now erase this so I can put a box around it. This is our first equation for an elastic collision, and this is our second equation for an elastic collision. And so we use those two equations, and we can calculate what goes on in a collision. So in a problem, we have two possible equations. If it's inelastic, V1 final equals V2 final, and momentum is conserved, so M1, you know that. If it's elastic, we have the same constant of momentum, and the sum of initial final for car 1 is equal to the sum of initial final for car 2. So that means in both situations, we have two equations. We have 4 unknown speeds. So if they give us 2 unknown speeds and the 2 masses, then we'll have 2 unknowns for 2 equations we can solve. There's actually a total of 6 unknowns in a collision problem. Mass 1, mass 2, speed 1 initial, speed 1 final, speed 2 initial, speed 2 final. So they still have to give us 4 of those 6 variables for us to be able to solve it using these 2 equations. And you know what? Solving collision equations is really not that fun. A lot of the problems you've had make it simpler, where they give you like all but one of the variables. If they give you all but one of the variables, then you can just use conservation of momentum in one equation and solve it. If there's 2 missing, then you're going to have to use the second equation. Okay, that is my review of collisions. Are there any questions about collisions before we get to today's lab? While it's in my head, the sound was garbled for my lecture yesterday. I tried to reset things, clear up disk space on this, rebooted the computer. It was still garbled for my lecture this morning. Not sure what's going on, but I'm trying to figure that out. So if you're watching the videos on YouTube, I'm trying to figure out why the sound is being garbled. Hopefully, get that straightened out. Okay, for today's experiment. You're going to be exploring collisions. And so you have one thing you really need to know is that kinetic energy, 1/2 mv squared, can be written in terms of momentum. I was working one of the homework problems with a few students, and working the homework problem, you had to use the relationship between kinetic energy and momentum. And oftentimes we realize, okay, so momentum, mass times velocity, kinetic energy, 1/2 mass times velocity squared, we have the same two variables in there. But we don't often realize that means that we can write kinetic energy in terms of momentum in a simple fashion. So there you see that using the fact that momentum is mv, that means v is momentum over m. And just substitute momentum over m into 1/2 mv squared, and you get the kinetic energy momentum squared divided by 2m. So that's an equation that, well, yeah, you need to use for the homework that's due, was it tomorrow, right? Yeah. Okay, for today's experiment, you need to have an observation that deals with a one-dimensional collision. One-dimensional means straight line. So we wouldn't have, I'm running along and I hit Irving and Irving goes off the data angle and I go off the data angle. That's two-dimensional. It needs to be straight line. And then you're going to explain something about that collision using elastic or inelastic collisions. So you say, this collision is elastic because of this. And then your test of the hypothesis will say, okay, so, if it's an elastic collision, because of that, then I should be able to do other types of collisions that have whatever that was. And if it's elastic, they should have the kinetic energy conserved. Or if you say it was inelastic because of this, then I should be able to test other types that fit this and see the kinetic energy wasn't conserved. So that's the way the hypothesis is tested. In the test, you need to specify what your specific experiments are going to be. So I'm going to have two carts, and I'm going to have cart A have this mass and hit cart B that has this mass, and B will have this initial speed compared to A. Specify what you're going to do for your collisions. Now, for the experiment, you need to do a skeleton, a minimal setup to make sure you have everything going, you know what you're doing. I say minimal. It involves, I think, 2 collisions per person in your group. I think that's what it requires. I didn't read over carefully. So you set up your equipment. Here I set up the Pasco equipment. You have 2 carts. Here's something important to note. I have one sensor plugged into port 1, one into port 2. One that's in port 1, my computer believes is cart 1. So I'm going to measure the mass of cart 1, and the one that's closest to the sensor is always cart 1. So make sure the one that's identified, this is cart 1, is always closest to that sensor. The one you identify as cart 2 needs to be closest to the one that's in port 2. Now, let me just switch over to the Pasco software. So the Pasco software, oh yes, we can see we've lost 407 seconds of audio in today's talk. That's 6.5 minutes of audio. It's going to be garbled again. I don't know what's going wrong. Try to restart recording with lower resolution frame rate. That's the next thing I will do. Okay, close that. So here is the basic setup. We have momentum in the top graph, and we have kinetic energy in the bottom graph. Notice there's P1, that's the momentum of cart 1. P2, that's the momentum of cart 2. P total is the sum of the momentum between the two. Now the first thing I'm going to do is just put one car on the track. I tried to set these, both of them are set to the cart setting, and I tried to make them so it's shooting across. And I'm just going to check and make sure that it sees the cart going all the way across. So record. And now, of course, you will have leveled the track and everything. Right? Right. Now, You would never print a graph like this. Why not? Yeah, I need to scale it because this right here, that is where I stopped with my finger. That's not even part of my data. So what I'm going to do here is I'm going to select data, which I think is that button. I thought it was that button. There we go. Probably put, yep, it did. It put 2 on there. And so I'm just going to select the data from when I started until just before I stopped with my finger, and auto scale to that. Okay, so the kinetic energy, you can see here's where I pushed it. What's this little thing here? The truth is I don't know. I do not know what that is, but it randomly occurs sometimes. You see, it's only one of the sensors that picked that up. The other one didn't. It's a flaw in the equipment. You can't control a flaw in the equipment. Now we can see here, I need to scale this better because I don't care about anything except for, okay. I don't have a delete button here, so I guess I won't delete it. There I see only the data that mattered to me. So look at that data that mattered to me. What happened to kinetic energy? What was it doing? Decreasing. Why? Friction was making it come close to rest. So there is some friction. That's why this had a general downward slope. Because of that, when you do an experiment and you actually have a collision, you're just going to look to see if it maintains the same slope through the collision. Because it won't be exactly the same because there is friction. Now let's zoom this one. Okay. I forget that it's a different method. Now notice in these, I have 2 carts right on top of each other and one that's double. That's because momentum 1 and momentum 2 should be the same. And so the total momentum is twice that. So we can see that that all works great. Now I'm going to do a collision. And the collision, I'm not going to do it correctly because I don't want people to already know what it's going to look like. So what I'm going to do is I'm going to have one cart that does not have the bar, one cart that does. They're different masses. My computer is set so it's going to calculate as if they're the same mass. So it's going to give you the wrong calculation. So that's why it's not going to look right. So I'm going to have one cart hit the other. Okay, experiment done. Now we need to analyze this. How do we analyze it? Well, I want to adjust my scale so I can see what each cart was doing. So I look at this, and I have the, what would you call that, magenta cart, which is cart 2, because I see over here from the legend that that's cart 2, was initially moving with a negative speed, whereas cart 1 was stationary. They collided, and cart 2 went to a slower speed, and cart 1 went to a speed that was faster than the original speed for cart 2. What happened to the momentum here? Did the momentum stay constant? No. What happened that makes no sense at all? The momentum increased. Could the momentum really have increased? No, that violates all of our physics. What's wrong? I told you what's wrong. It has the wrong mass. Let's look at the kinetic energy, and we see a similar tale. It says that we gain kinetic energy during the collision. Now, for analysis, you want to identify where the collision occurred and just have about 3 data points before to 3 data points after. So there's about 3 data points before. There's about 3 data points after. Sorry. You want to change your scale to something like this for your analysis so you can see, this is what happened. We don't care about all the stuff before the collision or all the stuff after. And so now we look and we say, this blue line did not appear to stay constant. It went to a bigger magnitude negative momentum. This line here did not appear to stay constant. Now I will do something I said I wouldn't do. You are going to do experiments with different masses. How do I take care of that? You click the calculator and it shows you all the calculations. Momentum 1 is mass 1 times velocity 1. Kinetic energy is momentum 1 squared divided by 2 mass 1. Simple stuff. But then we have, what is mass 1? Mass 1 is set to 1, and mass 2 is set to 1. Well, in reality, mass 1 was 1/2 kilogram, and mass 2 was 1 kilogram. So I need to change this, which without a keyboard is hard. The one that's part 1 is this. So part 1 is 1/2 kilogram. So I'm going to change this from 1 kilogram to 0.5 kilograms. Got to hit enter so it gets saved. I'll close this up. And you see the graphs changed. Now you look at momentum. It also changed my time frame. So I need to go back to get just the time frame I wanted. Look at the momentum. Now it looks like that line is just a continuous slope. So was momentum conserved? Within the effects of friction, yes, because that slope was consistent. Now, if we look at the kinetic energy was going like this. It dipped, but it came back up. So if we look at this and we take this line and continue it on, it does match up. So we say the kinetic energy was also conserved because it stays on that slope. Now, what was going on right here? We definitely lost some kinetic energy there. What happened? It went into potential energy. In this case, it was magnetic potential energy. But magnetic force is a conservative force. It gave us back the energy to make it so we ended up with the same kinetic energy as we started before the collision. So that's how you're going to analyze to see if momentum and kinetic energy were conserved, by looking at the continuity of slope. Now, the slope after this is going to be different because you have different speeds, and that causes us to have slightly different frictions here. But if you follow that slope, it matches up roughly, then you say, yeah, it was conserved. Whereas if it goes like this and then it comes and it's down here instead of on that slope, then you say, it wasn't conserved, it lost energy. Any questions about how you're analyzing your experiments? Now, I strongly recommend don't delete your data until you're done. Just only look at. So to choose what data you look at, you click up here and only look at the most recent data or whatever. But keep it there so you can go back and check it out if you find you made a mistake, like you forgot to change the mass. It always happens. A few groups forget on the computer to change the mass when they change the mass on the actual experiment. So keep the data there, so go back and change the mass and say, oh, wait, it was like that. Okay, going back to the experiment then. This tells you, first one is just the one I did. And so you can actually already answer these questions based on what you're supposed to do it yourself. You label each one, record the mass of your report with uncertainty. Now, I've been grading the labs. I'm looking for something to help me because I'm hopelessly lost in this grading. You'll need to measure the mass of your cards. Some of them people have written masses in there. They may be right, they may be wrong. Check it for yourself. When you check the mass, what's the first thing you do? Zero the balance. Don't trust the person before you zero it correctly. Believe me, a lot of people did not zero it correctly last lab where we measured mass. So make sure you zero it correctly. Then you put your card on and you measure the mass. How many decimal places should you have when you measure the mass? It measures 1, and so you should estimate a second one. You should have 2 decimal places for the mass. Your mass should be x.yz, well, it's actually going to be very close to 500. So let's say 501.YZ grams. And then you need to have an uncertainty with it. What if that Z, what if the last digit is 0? What do you do then? You write down the 0 because it's meaningful. A 0 means something. A blank doesn't mean anything. So you need to have 2 decimal places in your measurement of the masses, not just one. Because you're measuring the masses of each part. These here really should be very uniform at 500 grams, so don't worry about measuring this. Just call it 500 grams. You saw how you changed the mass in the computer. And I will do it again just because you may not have realized when I was doing it important. To change the mass, you click the calculator. The top 2 are the masses. You click in there. You actually have to click a second time, and then you just type. Make sure you hit enter so it's saved. The first actual experiment you're going to do is place the Velcro sides so the Velcro sides will hit and the cards will stick together. This is why you actually have 2 different types of cards. This card is called collision card. Nope, dynamics card. This one's called the collision card. It has the plunger. Seems like that's all, except for it has magnets on this side, no magnets on that side. So when you turn it so the plunger side is going to hit, then the Velcro will stick together and you won't have magnets to repel. So for your first trial, you're going to have it like this. They stick together. What kind of collision is that? Completely inelastic. So you're going to do a collision like that for the first one. Now, when you do this, before explaining, you think we'll observe if you send the cart 1 traveling toward a stationary cart 2, and they stick together, including a specific statement regarding whether you anticipate momentum and or kinetic energy to be conserved. Sketch what you think the graphs are going to look like. They don't have to be perfect. You don't need to spend 5 minutes on writing the graph, right? It should be quick. Make sure that your graphs have a useful title. I know I've emphasized this a lot, but in my grading, I've seen people who still say, momentum versus time graph. Well, I can read the axes. If you properly labeled it, you're going to have momentum on the vertical axis with its units, time on the horizontal axis with its units. I can read this momentum versus time. That doesn't help me one bit. The title needs to be something that tells me what's important here. So I'd say, collision between 2 cars having, same mass, one initially stationary. Something like that. That tells me exactly why this graph is useful to me. Okay, then you're going to do it and determine if you had the momentum and kinetic energy conserved. You'll print a graph for your laboratory report. When I say print, of course, I mean take the screen capture, and then you can save that PDF and insert it into your report. Before doing an experiment, now you're going to change to completely elastic. So completely elastic, I take this one and flip it around. Now the magnets will interact and they won't touch. If they touch, you should hear the click, and that one I don't count because they hit. Also, of course, if they're supposed to be inelastic and they bounce off of each other, you had some. This has what we like to call Velcro. It's technically called a hook and loop system. You have this side here has little hook things, and it gets caught in those loops and holds it together. And you absorb energy with that stuff flexing. And so that's what makes it completely inelastic. You're losing energy to the flexing of Velcro. Okay, so you do another trial with them sticking together, and then you're ready to test your hypothesis.